In this video, we'll be talking about degenerate perturbation theory. First, we'll start with a review of perturbation theory. Then we'll talk about twofold degeneracy, how to lift it, and then higher order degeneracies. So, remember, for a perturbation theory, a full Hamiltonian includes a solvable portion, that's something you can deal with analytically, plus a small perturbative component. And that is written generally as H equals H0 plus H prime being the perturbative component. If we expand the energy and eigenfunction solutions of this full Hamiltonian in the same way, but with an order, higher order terms, that is, E sub n is E sub 0, the unperturbed energy, plus a first order correction plus a second order correction. And similarly, the wave function has the 0th order, that is the unperturbed wave function plus the first order correction, and so on. We can obtain the first and second order corrections to the energy by solving a series of these equations with different orders of magnitude. So this being small, small, and small squared, for example. The first order correction to the energy is simply the expectation value of the perturbing Hamiltonian with the original unperturbed states. The first order correction to the wave function is a sum over all the other wave functions besides the one that we're interested in, because that is already in the first term here. So this term has all contributions from all the other unperturbed wave functions except this one, the unperturbed nth state. And it's a sum of the matrix element H prime mn, where m is psi of m0 and n is psi of n0. And then you have the energy denominator, which is E sub n0 minus E sub m, and then you have the unperturbed wave function psi m0, and you sum over all the m's that are not equal to n. The second order correction to the energy is similarly a sum, where m is not equal to n, but now you have the matrix element squared, modulus squared, divided by the energy denominator. So this is now a scalar, this is clearly a function. Now this works fine, except there's a big problem. And the big problem is what happens with degenerate states, where the energies are the same, when the energy denominator varies. That is, if you have n is degenerate with another state m, then this energy denominator vanishes, and the first order correction to the wave function goes to infinity, as does the second order correction to the energy. And in addition, this term will be 0. So the simplest case that we can deal with is a twofold degeneracy, where you have two states that have the same energy, and we can find the linear combinations which properly solve the total Hamiltonian. So we denote the two degenerate states as psi A0 and psi B0. These are two states with the same energy, but they're orthogonal to each other. And they have associated eigenvalue equations. That is, H0 applied to psi A0 is equal to E sub 0, E0 psi A0, and H0 applied to psi B0 is the same energy, E0 psi B0. Well, if we apply the full potential, which we call H plus H0 plus lambda H prime, and let lambda go to 1, so we're going to apply the full potential, the degeneracy has to be lifted, right? If we start with lambda equals 0, this is the unperturbed Hamiltonian. As we allow lambda to go to 1, then you get the fully perturbed Hamiltonian. And the degeneracy is lifted, and what happens is the energy starts at the same position. But as you turn on lambda and goes to 1, you'll have one state that goes down, one state that goes up. But it's not necessarily psi A and psi B. You have to find what combination of psi A and psi B will give you the psi plus and psi minus that fit the proper, that give you the proper orthogonal split states in energy. In general, if you postulate that you start with a good state up here and a good state here that are orthogonal to each other and have different energies, as you evolve them back, where lambda goes from 1 back to 0, then these two states will end up in two good linear combinations of the original degenerate states that can be solved by perturbation theory. That is, psi plus is some constant alpha times psi A0 plus beta times psi B0. And psi minus is gamma psi A0 plus delta psi B0. So these two combinations would give you the properly orthogonal states that have two different energies when lambda goes to 1. That is when you have the full perturbation. And that means that when you apply the unperturbed Hamiltonian to psi plus minus, of course you get E0, but you get psi plus minus back. So they're also eigenfunctions of the original Hamiltonian. Furthermore, these eigenfunctions are equal, the inner product of these two eigenfunctions is equal to 0 because they're orthogonal to each other. So the task we have is to determine the good combinations which we don't know in advance. So what we can do is, instead of working with both psi plus and psi minus, let's assume a generic solution. The generic solution, psi 0, is alpha psi A0 plus beta psi B0. What we're going to do is we're going to solve the full Schrödinger equation. The full Hamiltonian applied to psi is equal to E psi by expanding the wave function and the energies to higher perturbative orders so that we can solve this exactly. So we start with the Hamiltonian, which is H is equal to H0 plus lambda H prime. Psi is equal to psi 0 plus lambda psi 1 plus lambda squared psi 2. And E is equal to E0 plus lambda psi E1 plus lambda squared E2. So these are the second order terms, first order terms, and zeroth order terms. Well, again, we apply our eigenvalue or Schrödinger equation, H psi equals E psi, because this is now the new energy of this good state, which is going to be a linear combination, a generic state. We should get two solutions. We'll get one which is psi plus and one which is psi minus. So we will now apply H psi, and we have to expand it. So H and psi gives you H0 psi 0, that's the first term. Then you have lambda times H0 psi 1 and H prime psi 0, these two terms here. And we're only going to keep the first order terms in lambda. So the rest of the terms are all higher order. On the right side, we have E psi, and there we have E psi 0, E0 psi 0, which is this term. Then you have E0 psi 1, which is the first order term with lambda. And you have psi 0 E1, which is also a first order term in lambda. The rest of the terms have higher orders of lambda. So we now look at these two and we realize that the zeroth order term is just the eigenvalue equation for the unperturbed system. What we're now interested in is in the first order terms. And that gives us that we have a Schrödinger equation to solve, which is H prime psi 0 plus H0 psi 1 is equal to E1 psi 0 plus E0 psi 1. We can drop the lambda because it cancels out on both sides. Well, that's the equation that we have to solve. We're first going to apply psi A0 and close the inner product on this equation. So we apply psi A0, the bra, to all of these. Well, that gives us four terms. psi A0 H prime psi 0 plus psi A0 H0 psi 1 equals E1 psi A0 psi 0 plus E0 psi A0 psi 1. Now remember, psi 0, our generic solution here, it's a linear combination of psi A0 and psi B0, has coefficients alpha and beta. So when we close this and we put in this value here of psi A0, we'll get two terms for each one of these two here. And then we have left our psi 1. So let's expand that. The first term gives us psi A0 H prime alpha psi A0 and psi A0 H prime beta psi B0. The second term remains the same. It's psi A0 H0 psi 1. And on the right side, we have E1 psi A0 alpha psi A0 plus E1 psi A0 beta psi B0. Now remember, beta and alpha are constants, so we can, and then you have the third term over, the fourth term over here, which remains unchanged, which is E0 psi A0 psi 1. Well, the first thing we can do is pull the beta out here, and we can move the H0 over to this side because it's a Hermitian operator. So when we move this over to this side and apply it to psi A0, we get E0 out here. The E1 moves out of this, and the beta is out of this as well. And now we have an inner product here, which is 0. And we have an inner product here, which cancels out this inner product here, which is psi A0 psi 1, psi A0 psi 1 times E0. So we can cancel three terms out because these two cancel, and this is equal to 0. We now can pull out the constants alpha here, and beta here, and alpha from here. So we get alpha times psi A0 H prime psi A0 plus beta times psi A0 H prime psi B0 is equal to alpha E1 psi A0 psi A0. Well, clearly this term is equal to 1. This term is simply the matrix element, the diagonal matrix element of H prime along, it's the diagonal element for A and A. So we get alpha WAA, which is this matrix element, plus beta times the off-diagonal term, which is the AB term. So this is matrix element WAA, matrix element WAB. And that's equal to alpha E1 because this inner product is 1 rather. So our notation is that Wij is just the matrix element of H prime with psi I0 and psi J0, where I and J can be A and B. We can now do the same thing and close this same equation up here with psi B0. And we get basically the same situation. We have four terms, psi B0 H prime psi 0 plus psi B0 H0 psi 1 plus E1 psi B0 psi 0 plus E0 psi B0 psi 1. Again, putting in this value for psi 0, we could immediately cancel out this term and this term because the H0 goes over here and gives us the same matrix element. We can then expand this term and this term, realizing that the cross product, that is the term that has psi B0 and psi A0, goes to 0. So we're left only with the psi B0 times beta, E1 on this side. And on this side we have two terms, alpha psi B0 H prime psi A0 from here, and then beta psi B0 H prime psi B0 also from here, but the second term of psi 0. Well, this is simply the two additional matrix elements. This is WBA and WBB. And this tells us that since this is 1, you get alpha WBA plus beta WBB is equal to beta E1. So we have two equations, this one here and this one here, and we should be able to solve for our coefficients alpha and beta. These are the two equations. We can solve for the energies of the ideal states, E1. Well, we start with this equation here. WA plus beta WAB is equal to alpha E1. And we're going to solve for WAB. So we get beta times WAB is equal to alpha times E1 minus WAA. That means we can now take and substitute a WAB, and multiply WAB, all these terms, by WBA. So we're going to multiply each one of these three terms by WBA. So we have alpha times WAB WBA, that's this one. Then we take this equation and we multiply all of them by WAB. So alpha WAB WBA plus beta WAB WBB equals beta E1 WAB. So the first equation we transform like this and we solve for WAB. The second equation we multiply times WAB everywhere. We can now solve for alpha WAB WBA, bringing all the other terms to the other side. We get beta WAB times E1 minus WBB. Remember, WBB, WAA are the diagonal elements. Well, with these two equations, we can now combine them by solving for, by plugging in for W beta times WAB right here. So we have alpha WAB WBA is equal to alpha E1 minus WAA times E1 minus WBB. If we assume that alpha is not equal to 0, because that would be sort of a trivial solution, we can solve for the energies now. This is just a quadratic equation. So when we multiply this out, we get E1 squared minus E1 times WAA plus WBB. That's from this cross term and this cross term. Then we have plus WAA times WBB. And when we bring this one over to the same side, we get minus WAB WBA. And the alpha, of course, goes away. So 0 is equal to this equation here, which is simply a quadratic equation, which we can solve by the quadratic formula. So we have two energies which solve this equation. E plus minus 1, so the plus and minus terms, are equal to 1/2 times WAA plus WBB plus or minus WAA plus WBB quantity squared minus 4 WAA WBB minus WAB WBA. If we now recombine what's under the square root and realize that we get, if we square this out, it will cancel two terms. There will be a term that's canceled, and we can rewrite this in a very simple way. So E plus minus 1 is equal to 1/2 WAA plus WBB plus or minus the square root of WAA minus WBB squared plus 4 times WAB modulus squared. So we assumed that alpha was not equal to 0 to get that solution. But what if alpha was equal to 0? What would we get? Well, remember we had two defining equations. Alpha WAA plus beta WAB is equal to alpha E1, and alpha WBA plus beta WBB is equal to beta E1. Let's suppose that alpha is 0. Then this is 0, this is 0. Then beta WAB is 0. And that means that this term here says that WBB is equal to E1 minus. If we now set beta equal to 0, then we get the WBA is 0, and you get E plus 1 is WAA. So if alpha is equal to 0, or if beta is equal to 0, then what we have is we have already diagonalized the solution. So these are simply the non-degenerate first-order perturbation results. And it means that psi A0 and psi B0 are already the ideal states. So if the off-diagonal elements are 0, then you've already have the right states. Because WAB is just a matrix element of psi A, H prime psi B, and if that's 0, then the matrix is just diagonal. So if we could choose the right or the ideal linear combination right from the beginning, then it'd make our life simpler. We wouldn't have to solve it. And in fact, there's a way of doing this. So you can determine alpha and beta if A is a Hermitian operator, which commutes with both H0 and H prime, and psi A0 and psi B prime are also eigenfunctions of A with distinct eigenvalues. Remember, if we have an operator that commutes with the Hamiltonian, then you can have common eigenstates. So let's presume then that the common eigenstates psi A0 and psi B0 are the common eigenstates of A and H0 and H prime. So we can now write an eigenvalue equation for A and psi A0 gives us an eigenvalue of mu psi A0. And A applied to psi B0 is going to give us a different eigenvalue, nu, times psi B0, where mu is not equal to nu. In this case, because these are already eigenvalues, these are the right eigenvalues, eigenfunctions for diagonalizing H prime, then by definition WAB and WBA are equal to 0. This is the theorem. So we'd like to prove that. So A and H prime commute. So because A and H prime commute, then we have AH prime minus H prime A is equivalent to 0. If we take the inner product, or this inner product, where you have psi A0, commutator of AH prime, psi B0, this must be equal to 0 because the commutator is 0. But let's look at what happens when we expand the commutator. So if we expand the commutator, we get psi A0, AH prime, psi B0, minus psi A0, H prime A, psi B0. If we now take the H prime and the A, we'll take the A and move it over to this side and apply it to psi A. And we apply the A directly to psi B. Well, when we apply the A directly to psi B, because of this eigenvalue equation, we get nu times psi B0. It's just a constant. When we move the A over, because it's Hermitian, it remains the same. And you then can apply it, and you get mu psi A0, H prime psi B0, minus psi A0, H prime nu psi B0. Well, the mu and the nu come out. So mu minus nu times this expectation value, this matrix element here, or this inner product, psi A0, H prime psi B0, must be equal to 0 because it's equal to the expansion of what is defined as 0 because the commutator is 0. Well, what this means is if mu and nu are not 0, this is simply the matrix element, the off-diagonal matrix element. And what this says is that if mu is not equal to nu, then the off-diagonal element must be 0. So we'll use that occasionally to be able to find the right combination of of wave functions to normalize and to diagonalize H prime. Now the final thing to look at is if you have higher order degeneracies, then a matrix formulation is much more useful. Let's look at the two-dimensional case and sort of look at it as if it's a matrix. So recall the two defining equations that we had. Alpha WAA plus beta WAB is equal to alpha E1, and alpha WBA plus beta WBB is equal to beta E1. We can rewrite them in form of a matrix. The matrix being WAA, WAB, WBA, WBB multiplied times the vector alpha beta is equal to E1 alpha beta. Right? And that defines these two equations. Let's see how that works. If you take WAA times alpha and WBB times beta, when you take this row and multiply it times this column vector, you get the first equation, E1 times alpha. When you take the second row, WBA, WBB, and multiply it times the column vector alpha beta, you get E1 times beta, which is the second equation. So this is simply a rewriting of a matrix equation that looks like this. And you can see that if you have many states that are degenerate, not just two, it's much more convenient to work with a matrix formulation because you can diagonalize a matrix. So the E1s are the eigenvalues of the W matrix. If we know the W matrix, we can calculate it. We can diagonalize that matrix and calculate the eigenvalues. And the good linear combinations of the unperturbed states are the eigenvectors of this matrix, once you've diagonalized it. So all that we've done so far is basically a 2x2 diagonalization. So Wij is equal to psi I 0, H prime psi J 0. And this is the matrix that we have to diagonalize. So when you have more than two states, this can be a very useful way of formulating the system. You can prove, in problem 713 in Griffiths, this can be proved by assuming that you have a set of unperturbed eigenfunctions, psi I 0, which are n-fold degenerate. So the eigenvalue equation for each of these is H0 psi I 0 is equal to E0 psi I 0 for all values of this n-fold degenerate system, and they're all orthogonal to each other, orthonormal actually. And psi 0 then is the general combination of all these particular states. Sum of I equals 1 to n, alpha I psi I 0 gives us the eigenfunctions that we're interested in, the general state. But you'll have, if you have an n-fold degenerate, you'll have n solutions to this, each of which has a split energy.